4.5 is on the multiplication rule, complements, and conditional probability. The probability of at least one. So what does that mean? Let's say that there were 5 births that some family had. So they're either going to have a boy or a girl for each birth. And what's the probability of at least one boy? It's definitely, I guess, not as cut and dry as you would think it would. Or conditional probability. We know what is the probability if the first 4 births were girls, that the 5th birth will be a boy. It really depends on a couple of factors, but that may be a trick question. No matter what the first births were, the 5th birth, there's a 1 in 2 chance it'll be a boy. But we're going to think about things like that today. The complement of at least one. So we have the probability of at least one. The complement of that is equal to the probability of none. So the complement of at least one means the probability of none. Okay. So that works both ways. The probability of not none would be the probability of at least one. Remember, at least one means one or more. So if we know that at least one and none are complements of each other, then the way that you can find, one way that you can find the probability of at least one is by saying 1 minus the probability of none. Why is that? Remember, the probability of event A occurring plus the probability of it not occurring is equal to 1. So if we want to find the probability of something occurring, you can say 1 minus the complement. And that's what we do here. If we want to know the probability of at least one, then you can say that's the same thing as, or that's equal to, 1 minus the probability of none. Alright, and we'll use that to help us find some probabilities. In the same respect, depending on the information given, if you want to know the probability of none, that's the same thing as 1 minus the probability of at least one. Now that will probably not be used as much. Usually we will be looking for the probability of at least one, and somehow we can easily figure out the probability of none. Alright, so this first way that I wrote down, that's usually how those complements are used. Okay, and that's what your book goes through here on page 168, is on how to find the probability of at least one of some event. Alright, so let's just really quick read through this example here in the text. Top for Development supplies X data DVDs in lots of 50, and they have a reported defect rate of 0.5%. So the probability of an individual disk being defective is 0.005. It follows that the probability of a disk being good is 0.995. That's because if you say 1 minus 0.005, you get 0.995. If a quality control engineer wants to carefully analyze a defective disk, what is the probability of getting at least one defective disk in a lot of 50? Okay. Is the probability high enough that the engineer can be reasonably sure of getting a defective disk that cannot be used, or that can be used for her analysis? Alright, so if we want to know the probability of at least one of the 50 disks is defective, then what would the complement of that be? Your book says identify the event that is the complement of A. So if A is at least one of the 50 disks is defective, not A would be not getting at least one defective disk among 50. Or the probability that all 50 disks are good. Alright. So find the probability of the complement. Right here, the probability of not A, or the probability that all the disks are good, would be 0.995 raised to the 50th power, because there's 50 disks. So each one of those you'd have to multiply. And if you do that in a calculator, you get 0.778. Alright, so this right here is the probability that all 50 disks are good. So if we want to know the probability that at least one of the 50 disks is defective, then we say 1 minus the probability that none of them are defective, or that they're all good. And so if you say 1 minus 0.778, that's 0.222. All right. So that's at least one, and its complement, none. Let's take a look now at conditional probability. With most types of probability, there's a classic approach, and then that's for people that just want to mainly stick to formulas no matter what. And then there is an intuitive approach, which kind of means how could I use common math sense to work this problem out? Sometimes working it out by the formulas will be easier. Sometimes working it out just trying to make sense of it will be easier, depending on the how complicated the problem is. All right, let's look at conditional probability. This is one of those such times when we have two ways of really looking at things. The conditional probability of an event is a probability obtained with additional information that some other event has already occurred. So if we have P of B and then a vertical slash and A, that denotes the conditional probability of event B occurring given that event A has already occurred. So the probability of B given A can be found by dividing the probability of the events A and B both occurring by the probability of event A. So using a formula, you can find the probability that B occurs given A is equal to the probability of A and B occurring over the probability of A occurring. Now, intuitively, your book says finding B given A. We can find that conditional probability of B occurring given that A has occurred. It can be found by assuming that event A has occurred and then calculating the probability that event B will occur. Okay? So what's the probability of a couple having a boy on the 5th birth if the first 4 births were girls? Well, the probability of the 5th birth is going to be the same as the probability of any birth. 1 out of 2, right? Assuming that boys and girls are born at the same rate, 1 out of 2. All right. Let's look at example 2 here. This goes back to the chapter problem. We're talking about that drug screening results. Well, we had our true positives and false positive, false negative, and true negative. All right, let's look at example A. If one of the 1,000 test subjects is randomly selected, find the probability that the subject had a positive test result given that the subject actually uses drugs. That is, find the probability of a positive test result given subject uses drugs. I'll make a copy of that real quick so we can work it out. Alright, so let's try to work this out, part A, using both methods. Using the intuitive method by just trying to make sense of it. And then let's work it out using the formula, just the strict, I only want to use formulas type way of thinking. Alright, so first let's look at it intuitively. We want the probability of positive test result given the subject uses drugs. Okay. So if we look at this table, positive test result here, right? Here's the positive test results. Given subject uses drugs. Here's subject uses drugs right here. This line. So where does that overlap? Right here at 44. There are 44 results that are positive test result and subject uses drugs. So intuitively we could say that's going to be 44 out of positive test result given that the subject uses drugs. Okay, so if we just assume the first part is already going to happen, or has already happened, we know it's a positive test result, then how many subjects uses drugs are there? 50. So the answer is 44 over 50. That's how we can think about it, you know, kind of with a math sense. This has already happened. The first part has already happened. We know that it's a positive test result. So just assume that's given. Out of all the positive test results, what's the probability of getting a subject that uses drugs? 44 out of the total 50. Now let's see how we could think about that using the conditional probability formula. Remember, the conditional probability formula the probability of B given A is equal to the probability of A and B over the probability of A. So we want the probability of positive test result and subject uses drugs. So positive test result and subject uses drugs. So I'm just going to say positive and uses drugs. That's going to be 44 out of how many? 1,000. Positive test result and uses drugs divided by, because there were 1,000 people in the study. So it's the probability of A and B divided by the probability of A. So remember, Here's B. Here's A. Using the formula, the probability of positive and uses drugs, that's 44 out of the 1,000 total, divided by the probability that the subject uses drugs. So how many total do we have that use drugs? 50 total, right? Subject uses drugs. 44 were true positive, 6 were false negative. So that's 50 out of how many total? 1,000. So we should get the same answer. Let's see. Remember, if you divide a fraction by a fraction, you have to flip and multiply. Okay. And of course, these can be reduced. You can write those as decimals. If you take a calculator and divide that, you get 0.88. All right, now let's look at B. All right, B says, if one of the 1,000 test subjects is randomly selected, find the probability that the subject actually uses drugs, given that he or she had a positive test result. Okay, so probability subject uses drugs. Given that we have a positive test result. All right, so let's think about that intuitively. So let's assume that the person has a positive test result. So you see, here are the people that have positive test results. Out of these people, what is the probability that the subject uses drugs? So how many people total do we have? 134. What is the probability that, or how many of them use drugs? 44. Part over total. So 44 over 134. If you divide that in a calculator, you get 0.328. All right, so let's see if we can do that not thinking intuitively by using the formula. So the formula, probability of B given A is the probability of A and B divided by the probability of A. So remember, this is B, this is A. All right, so what is the probability that the person uses drugs and has a positive test result? So uses drugs and positive test result. 44 out of how many? 1,000. Divided by, what is the probability that a randomly selected person has a positive test result? So how many people have positive test result? 40 plus 90, or 134. Take that and divide by 1,000. Now to work out this, you have to flip and multiply. Cancel out. You get 44 over 134, which again is 0.328. All right. All right, so let's look at maybe a couple of the problems from the back of the section, just to see a couple of different types of problems. Make sure that we understand what's going on. All right, so let's look at, say, starting with maybe number 6. Of course, we need to read those directions then. Let me go up a little bit. All right, describing complements. Number 6, provide a written description of the complement of the given event. So we want to write down the complement of whatever it says. Then find the probability of the complement of the given event. Okay, we can do that. So it says, when a couple has 5 children, none of the 5 is a girl. When a couple has 5 children, none of the 5 is a girl. Assume that boys and girls are equally likely. So we want to write the complement of no girls out of 5. So the complement of that, how could we write that out? That would be maybe at least one girl of 5 children. So we have at least one girl. That's the main thing. At least one girl. Okay, so we can find the probability of at least one girl by saying the probability of at least one equals to 1 minus the probability of none. All right. So we have to figure out a way to calculate the probability of none. We have 5 births. What's the probability that the first birth will be a boy? 1/2. Same second birth, 1/2. Third birth, 1/2. Fourth birth, 1/2. Fifth birth, 1/2. This is the probability of each birth being a boy, which is 1 over 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So that's the probability that there will be no girls out of 5 births. So the probability of at least one girl will be equal to 1 minus 1 over 32. Get a common denominator. So that's 32 over 32 minus 1 over 32, or 31 over 32. See what that would be as a decimal. 31 divided by 32, 0.969. If you round to 3 places, 0.969. So there's a 96.9% chance that out of 5 children, at least one is a girl. I have a friend who has 5 girls, no boys. So it'd be the same coincidence. The probability of that happening would be 1 out of 32 of him having all girls. All right, let's look at number 8. Let's go to the next even problem. So we want to write the complement of when 4 digits are randomly selected and replaced for a lottery ticket between 0 and 9 inclusive. None of the digits is a 7. So probability that none of the digits is a 7. So the complement will be what? At least one digit is a 7 of the 4, right? That's what it said. There were 4 digits. So if we want to know the probability of at least one digit, then it's going to be 1 minus the probability of no digit being a 7. So what's the probability that we get a 7 if we draw? Remember, we have 4 choices. 1, 2, 3, 4. It was from 0 to 9 inclusive, meaning including 0 and 9, so that's 10 numbers. The probability that we would get no 7. Let's do the none so that we can say 1 minus the none. Probability of getting a 7 is 1 out of 10. So the probability of not getting a 7 each time would be 9 out of 10. All right, so this is the probability of not getting any 7 out of 4 possible digits. So whatever 9 over 10 to the 4th power is. So in our calculator, we want to say 1 minus 9 over 10 to the 4th power. And that will give us the probability that we at least get 1 7 out of the 4. Alright. So 1 minus, we'll put 9/10 in parentheses. Then I'm going to raise it to the 4th power. Okay, so if I round that to 3 significant digits, that would be 0.344. So that's the probability that we at least get 1 7 out of the 4 numbers drawn. All right, let's see. Let's work one more. All right, let's look at another one of these birth problems. How about number 13? Now this one isn't one where we have to find the complement. It's an actual problem to itself. So that was just for 5 through 8. All right. In the United States, the true probability of a baby being a boy is 0.512 based on the data available at this writing. Among the next 5 randomly selected births in the United States, what is the probability that at least one of them is a girl? So the probability of at least one of the 5 births is a girl. So to find that, you can say 1 minus the probability no girls, which is, what does no girls mean? All boys. All right, so probability of a boy each time. Okay, so we need to figure that out. Well, it told us the probability of a boy in the United States of having a boy is 0.512. How many births? 5. So to find the probability of 5 boys, it's 1 minus 0.512 to the 5th. Now this part right here, this is the probability of getting 5 boys in a row. I just didn't actually write out the slots and say 0.51 each time. 1 minus will give us the probability that at least one of the 5 is a girl. At least one of the 5. All right.
So you're saying 5.2 times 5, that's just getting the boys.
This part right here is the probability of having 5 boys in 5 births. So 1 minus this will give us the probability of at least one girl. All right, to 3 decimal places, that's about 0.965. This is in the United States. I'm assuming there was some big study done and they figured out that the probability of having a boy was 0.512. Alright, so if we want the probability of finding at least one girl, or having at least one girl out of the 5 births, that's going to be the same thing as 1 minus the probability of no girls. Which, what does no girls mean? That means that you had a boy instead. So 1 minus the probability of having a boy all 5 times will be 0.965.